Okay, everybody, let's go ahead and get started with section 12.1, which covers relations and functions. Now, this section is pretty close to section 4.6, which we just covered. So, I mean, a lot of these notes are going to sound a little bit redundant, but we have gone through quite a few of these already. The definition of a relation is any set of ordered pairs. You know, just anything that you see where there's an x and a y is going to be considered a relation. Now, a function is a type of relation. So I guess you can almost make a flow chart in there. Function is a type of relation where each element of the domain relates to exactly one member of the range or element of the range. Vertical line test, I'm going to skip that. Okay, so if we're looking at number one here, we're looking for the domain. The domain is going to be the set of all x values. So if I just write them out, I've got a 4, I've got a -2, I have a 6, I have another 4, and I have a -1. Now that should tell you, when you have repeating x values, you don't want that to happen. You don't want that to happen. So this is not a function. Doesn't mean those numbers aren't relevant, but what it does tell you is that this is not a function. So if I were to write out what the domain is and kind of be more neat about it, the domain is going to be -2, -1, 4, and 6. You don't have to write repeats. The range is going to be the set of all the y values. So the y values are 1, there's a 3, there's another 3, so I'm not going to list that again. There's a 12, and then there's another 3. So there's really only 3 y values, a 1, a 3, and a 12. And again, like I said, this is not a function. All right, when you're looking at a graph, and this graph should have like arrows on the end of it. If you're looking at a graph, you're looking at, okay, what is the domain? Sometimes this is difficult for people to kind of figure out. But if you're looking at any linear type of graph, especially if it's not vertical, if we're looking at a linear graph, the domain is all reals. That's the symbol for all reals. The reason for that is because just pick any x, and there's a corresponding y value that goes along with it. So if I pick this x value right here, well, that corresponds to that point, which has a respective y value that goes along with it. So if we pick this, let's say the x is 0, well, that has a corresponding y value right there of 1. So the domain is going to be all reals. So another way to write that would be like -infinity if I'm using interval notation, -infinity to +infinity. You don't need to write a plus sign. And same goes for the range. You know, the range is all the possible y values. Like this y value has right there, you know, this y right here has a value right there on the line. This y right here, that has a value on the line. So this is going to be all reals as well. So you're just going to write -infinity to +infinity. Now this one right here, the domain, if we look at the domain, I think sometimes people look at this, they see that it looks like it's straightening out, but this is really going forever. This is never going to straighten out, nor is this right here. It's going to keep going and going. I'm going to be a little bit exaggerating right there, but it's going to keep going in that direction. Same thing right here. It's going to keep going in that general direction. I mean, it's going to go slower. It's going to go steadily in that direction, but it's not going to ever become vertical. So that sometimes throws people off. Just the way it looks like is, oh, it's going to level off at some point, and it doesn't. So again, this is all reals. You can say the domain of this is all reals, and so is the range. This part right here, it says determine whether each relation describes y as a function of x. And so if we look at this as a function of x, well, we have to be kind of careful with this one because for x, x has to be greater than or equal to 0. So we're stuck with that. I mean, I know we've talked about imaginary numbers where we can have like square root of -1 and all that, but the answer to that is an I, which is not a real number. We're looking for, if we're talking about domain and range, we're talking about what are the real number solutions to it. And, you know, if we're talking about that, then the imaginary numbers are not going to be allowed in there. So this one right here is a function of x as long as x is greater than 0, all right? And that would be the domain, basically. The domain is going to be all values of x such that x is greater than or equal to 0. I'm going to use set builder notation, but it's all the same. You don't have to actually write the domain for that one, but I did. Okay, for the next one right here, this one is a function. This is definitely a function. All right, this is not a function. It looks more like x is a function of y, but that's not how functions work. We want y to be a function of x. And that's going to be a function. Now the definition of function notation, you're usually going to see function notation written like this, where it's y equals f of x. And I talked about that before. Y equals f of x, which basically just means that y is dependent. Y is the dependent value, and x is the independent value. Okay, right on for number 9, this is a function. That's a linear function, 2/3 x plus 2. If I just use slope-intercept method, this has a y-intercept of 2, and it has a slope of 2 to 3. So I'm going to go up 2, right 3, and I'm going to go down to left 3 to figure out another point here. And so there you go. So what is the domain of all this? Well, the domain is going to be all reals. I'd say most, if not all, linear equations, linear functions, I should say, are always going to be all reals. And same thing for the range. Nothing's off the table there for the domain or the range. Now, really quickly, I'm going to go through some linear functions here. Linear function, you're going to see it written as f of x equals mx plus b. It's written in that format. Basically, like, we don't really write y a lot in functions, but it's going to be like this, like y equals, 3x plus 5, something like that. It could be y equals 2x, because if there's no constant, then you can assume that there's a 0 there, so you can put a plus 0 there, and then it's the y-intercept. So that's all there. Polynomial functions are a little tricky because sometimes they get mixed up with being a quadratic. But a polynomial function can have any degree to it. It could have, let's say, like ax to the 4th power plus ax to the 3rd plus ax. And notice I'm using a every time just because I don't want you to confuse that with quadratic. Squared plus ax to the 1st plus a constant or something like that. But you can have that, whereas a quadratic function is going to take the form of what we were doing before, which is ax squared plus bx plus c. So the highest degree of a quadratic function is only going to be the x squared, whereas a polynomial function can have any degree to it. The other thing too is the coefficients. You want those to be real numbers. Okay, now the rational function is going to kind of take this form, which, rational has ratio in it. And ratio just means fraction. If you're doing that, you've got the p, and this is kind of, I think, the textbook kind of format of it. But the function of x is going to be the p of x over the q of x. When we look at the domain of this one, we have to be careful that q of x, the domain can be all reals, except when q of x equals 0, because we don't want the denominator, of course, of that to equal 0. I forgot to mention what the domain was of polynomial functions, but the domain of the polynomial functions is all real numbers. And same thing for quadratics. A square root function is going to be f of x equals the square root of x, something like that. And the domain here, if you remember correctly about square roots and radicals in general, we want to make sure that x is all reals that are greater than 0, greater than or equal to 0. So we want x to be non-negative. If I said x has to be positive, then I'm not including 0, but we could say x is non-negative and get away with that. And then the cube root, see probably kind of a pattern emerging here, is going to be something like this. And the domain of this one, if you guys remember with cube roots, x could be negative or positive. So you can have all reals there. Okay, so now looking at number 10 here, we've got let f of x equal x cubed plus 3x squared minus 4x minus 7. All right, first of all, we want to figure out, is this linear? Is it polynomial? Is it a rational function? Well, it is polynomial. It's polynomial. What is the domain of f? Well, that's easy. It's going to be all reals. It's going to be all real numbers. We want to find the function of negative 5. So the function of negative 5 is going to be a matter of taking that f of x equation and then plugging it in. I'm going to put parentheses wherever I see an x. So there it is. The function of negative 5 is going to be negative 37. So we're going to look at the function, the g function of x and the h function of x, and we want to kind of figure out this. So we're looking for number 13, we're looking at the g function of m, which means I'm going to take the g function that is given, and we're just going to put an m wherever we see an x. So the g of m is, this one's pretty straightforward. You're just going to do negative 2 times m plus 5, and there's really nothing that you can do to that. So that is in its simplest functional form, I guess you can call it that. For this one, we're going to take the g function and we're going to put in a minus 1 wherever we see an x. So we've got, so the g function of a minus 1 is going to equal negative 2, instead of writing x, we're going to write a minus 1 in its place, plus 5. Now this can be simplified a little bit, so you get negative 2a plus 2 plus 5, and then you have a little bit with like terms. There it is. All right, now the h of w, that's going to be the first time we've used the h function, and what we're just doing for that one is we're just putting a w wherever we see an x. So the h function of w is going to equal w squared minus w plus 4. This one, again, we're going to use the h function. And we're going to put d plus 3, or wherever we see a w. So we're going to put d plus 3 squared minus, and then I'm going to put d plus 3 in parentheses, and then plus 4 right there. Just refresh your memory. D plus 3 squared means d plus 3 times d plus 3, which is d squared. That's 3d. This is 3d. And this is 9. And so that comes out to d squared plus 6d plus 9. We're going to distribute the negative there. So that becomes minus, I'm going to write negative 1d minus 3 plus 4. And now it just becomes a matter of putting all your like terms together. And there's only one d squared term, so I'm just going to write that out. And there's a number of d's, so there's 6d here, and there's minus 1d there, which makes 5d. We're done with those. And then your constants, you have 9 minus 3, which is 6, and 6 plus 4 is 10. And that's it. Now, steps to determine the range for a function, I think we did that up here. So we're not going to do it again. Number 17 right here, we've got, for the first one here, we want to pay attention to this is a rational function. And since we're dealing with a rational function, we definitely have to make sure that that is not 0. So if we set that x plus 3 to 0, well then x is going to equal negative 3. Now that's the only value of x that when you plug it in, it makes that rational function undefined. So this one's going to be, you could say, the range of it is going to be negative infinity to negative 3, and then the union of negative 3 to to positive infinity. Basically, that's a fancy schmancy way of saying that it's all real numbers except where x is not equal to -3. All right, number 18, same thing. We have a rational function, so our focus is going to be centered on that denominator. So what value of that denominator is going to make that 0? And so you just want to set it equal to 0. And then I'm just going to kind of go through this and solve it. And you get 4/3. All right, or 1 1/3 if you want to think of it that way. So the domain for this one is going to be -infinity to 4/3, union of 4/3 to positive infinity. This one right here, if you look at this rational function right here, there is no variable in the denominator. So that just tells us that this could be anything. The domain of this one is up in the air. It could be -infinity to positive infinity. There's no limit. The sky's the limit basically on that one. Same thing on number 20. The domain on that one is going to be all reals. If you can think of a number that x cannot be, then tell me, but there isn't. X could be absolutely everything. It could be 0, it can be pi, it can be even an imaginary number if you want it to be that, but there's no limit as to what, there's no constraints as to what x could be. Now this one, I know it doesn't look like anything much, but it's really just a linear function. You can just think of it as like that. You can think of it as, it's really no different than this equation. Y equals 1x plus 0. So the domain of that is going to be all reals. There's going to be no limit as to what that is. Same thing for number 22. There's nothing that x cannot be. So that's going to be all reals. Same thing for number 23. I'm going to use the shorthand symbol for all reals. Now number 24 is a radical function, a square root function. And when you have a square root function, we definitely have to be careful about what the square root is. And so x, the domain, is going to be all reals as long as x is non-negative. And then number 25 is a little bit weird because you already have a negative in the radicand. And if you add a negative in there, if we add a negative, like let's say we add -4, well then -4 really makes +4. So that actually has an answer that is plus or minus 2. If I were to just add a regular old number, like 9, well that's going to be square root of -9, which is plus or minus 3i, which we don't want to get imaginary numbers for domains. So the domain of this one is going to have to be all negatives. So it's going to be non-positives. So all reals as long as x is non-positive, meaning it could be 0 or less. And then for number 26, we're just going to solve that equation, set that equal to 0. And when you do that, you get 2z equals -4. And then you get z equals -4 halves. And then z equals -2. So if you have that, now we're not saying that's the answer, we're just saying that's one of our constraints. And we're saying that the domain is all reals except, not x, z cannot equal -2. For number 27, we're going to set that equal to 0. And there's your constraint there. So this is all reals, except where x does not equal -1. That's our domain. Our domain for this one is all reals. And same thing for number 29. Because that's a cube function. Cubic functions are always going to have that number in there. Now a square root function, when you graph that, it's going to kind of, if I do a input-output table, if we do an input-output table, I know that's usually x and y, but I'm going to put f and f of x. We all know that means y. But if we put in 0 as our input, well, what's square root of 0? Well, that's 0. All right, so you get that. Let's say we put in number 1. Well, the square root of 1 is going to be 1. If I put in 4, we're going to get out a 2. And that's all my graph kind of leads me up to. So like I can graph this. I got 0, 0. We've got 1, 1. And we have 4, 2. So typically, square root functions are going to take that general shape. They're going to look like that. Okay, so I'm going to throw in some inputs there. So we've got square root of 0 plus 1 is 1, and then that's going to be 1 still. Let's say we put in negative 1. It's going to go backwards here a little bit. Well, if I put in negative 1, well, negative 1 plus 1 is 0. So square root of 0 is still 0. If I put in, just kind of thinking ahead of here a little bit. Let's say I put in x is equal to 3. Well, then I can do 3 plus 1, which is square root of 4. And square root of 4 is 2. So you get 3 and 2. And let's say I put in like all right, and let's stop there. Now if I graph that, I'm going to graph this point first. So negative 1, 0. Negative 1, 0 is right there. All right, 0, 1 is right there. And then 3, 2 is right there. Now what this is priming us to do here is if you look and you compare that with what we had up here, it's basically the same graph. Now you notice this has a little bit of a shift to it, which is something that we're going to be talking about later. But this has a shift. It's basically just shifted over 1 unit. It's the same exact graph, except it's 1 over. And there's something about the way that that function is written that tells you how it will shift. And once you figure out what that shift is and what that number is that affects the shift of it, then it makes it really easy to kind of figure out a general outline of what these sketches are going to look like. All right, let's say we put in 0 for the cube root of x. Well, the cube root of 0 is still going to be 0. Zeros, like I think I've said this before, but zeros are really easy numbers to throw into your equations. All right, let's say we use a 1. 1 is sometimes an easy number to use too. Well, the cube root of 1, well, that's 1 times 1 times 1, so that's also going to be 1. All right, and let's say we use, for the next point, let's say we're going to use 8. And I'm kind of cherry picking the numbers I'm using here because I'm using perfect cubes. But the cube root of 8 is 2. Now Now, one thing that you're allowed to do is you're allowed to put negative numbers in there as well. Well, the cube root of negative 1, the cube root of negative 1 is also going to be negative 1. Because think about it, negative 1 times negative 1 times negative 1 equals negative 1. The cube root of negative 8 is going to be negative 2. Because negative 2 times negative 2 is negative 4, or positive 4. And positive 4 times negative 2 is negative 8. So that works. So now if I graph these, all right, we've got 0, 0, 1, 1 is right there. We have 8, 2. We have negative 1, 1. And the graph for cube root functions, a little bit tricky looking, but it looks like that for the most part. And those aren't going to be, I know I drew them so they look like that, but they don't ever get horizontal. I mean, they're forever going in this general downward direction. Same thing here. They're going up very slowly, but they are going up in that direction. And for an infinite number of numbers in that direction. Now I just remembered I'm totally neglecting doing the domain. Now the domain of this function right here, if you look at it, is going to be all the values of x, such starting at 0, going to a positive infinity. All right. For this one, the domain, since this had a shift of 1 to the right or 1 to the left, this has a domain of negative 1 to positive infinity. This one has a domain of all reals. Now this one, again, you might notice this number 32 and number 33 look very similar to each other. And so you can probably expect there's going to be a shift to it. All right, let's say x is equal to 2. Well, and if you do that, you're going to get 2 minus 2, which is 0. And the cube root of 0 is still 0. All right, you can get that. Let's say I wanted that to equal 1. Well, I could use 3. We can use 3 in there. And so if you do 3 minus 2, that's equal to 1, and the cube root of 1 is still 1. If I did this, let's say we used, let's say we wanted to make it 8, well, I can use 10. Well, that's going to be 10 minus 2, which is the cube root of 8, and the cube root of 8 is 2. There it is. Now I've got to be careful with the next numbers here. So if I want to make, let's say I want to make negative 2. Then I'm going to put a 0 here. Let's say I want to make, negative 1. If I want to make negative 1, I'm going to put a 1 there, because you can do that. So you can do 1 minus 2. Well, that equals negative 1. And the cube root of negative 1 is negative 1. All right, let's say I wanted to make, Let's say I wanted to make 10, but this time I want to make negative. Let's say I want to make negative 8 out of that. All right, so if I want to make negative 10, I should put negative 8 there. So if I do that, negative 8 minus 2, well, that equals negative 10. Oops, I don't want to do that. All right, if I want to make that negative 8, I'm going to put negative 6 there because negative 6 plus negative 2 is negative 8. And the cube root of negative 8 is negative 2. So now we have a fair amount of points that we can use to graph. So 2, 0 is going to be right there. All right, 3, 1 is right there. 10, 2 is right there. 1, negative 1 is right there. And then negative 6, negative 2 is right there. And you can kind of get a general idea of what it's going to look like as a shift. And there it is. And you can see like it looks very similar to the previous one, except it shifted over. Now notice it shifted over 2 to the right. And notice how this has a minus 2 there. All right. This one right here shifted 1 to the left, and that had plus 1 there. So the shifts are a little bit weird the way they work, if maybe you've caught on to that. Okay, so that does it for section 12.1.